Hey guys, it's Steven, and I'm back to talk more about building AI agents. I know. I'm kind of harping on this one. I don't know how many more videos I have in me on this particular topic. Probably this one and one more maybe. But in this video, we're gonna do the fun bits of building an AI agent. We're actually gonna make our agent interactive with the world. We're gonna give it the ability to actually take action outside of just responding with some text. So a brief recap, I won't belabor this too much, but we've basically come to the understanding that the anatomy of an agent is first and foremost, it has the ability to use a large language model. We have the ability to send some text to an LLM and get a response. The second piece of our agent is the prompt. So typically, the whole reason you would create an agent is to sort of organize conceptually what you're trying to accomplish with a specific identity, right? So it's not just, hey, I'm going to ask the LM to do something. It's, hey, as this agent, I want you to understand this is the circumstance we're in. This is the identity you have in that circumstance. Here's what your objective is. Here are the guardrails for accomplishing your task, etc., etc. So you typically have some very specific prompt engineering or context engineering that's associated with any given agent. And then today, what we're going to talk about and actually implement is kind of the last piece of the puzzle that, in my opinion, is really what sets the agentic AI that everyone's talking about now, apart from the generative AI that maybe everyone was talking about 18, 24 months ago. And that is this ability to use tools and functions. Now, conceptually, most LLM providers like Gemini, like OpenAI, like Anthropic have something like this now baked into the way they train their models and the way they expose their models over their API. So you can basically have a structured way to define to an LLM, hey, here are some tools, here are some functions you can use, here's the information you need to provide in order to make use of these tools and functions, and you need to provide that back whenever you want to use it. But conceptually, a tool or a function is just code that you as the developer or you as the engineer, whoever is building the agentic system has written. They've implemented some, most of the time, deterministic code that takes some inputs, performs some sort of action, and returns an output optionally. So again, this is your ability to tell the LLM, hey, your job is to do XYZ based on this prompt. But in order to accomplish XYZ job, you can use these tools or these functions that we've provided to you. Remember though, the agent isn't actually running this code. They aren't running these tools. They aren't running these functions. They're just calling them, which means all they do is they return a response that includes the inputs they'd like to put into that tool or into that function to do whatever that tool or that function does. So that's what we're going to implement today. So first and foremost, let's just get a handle on what this looks like from the Gemini API perspective, and then we'll go in and actually look at implementing this in code in C#. So first and foremost, this is how Gemini implements function and tool calling. Is basically, in addition to the existing content that you're giving the model to generate a response to, you're also going to declare an array of tools. The array of tools can have a few different shapes, but one of the things it can have is a function declarations property. Now, this functions declarations property then declares an array of actual functions that the model can provide inputs to. And you can see how we define a function or how we define a tool to the Gemini model or through the API is we give it a name, we give it a description, and then we give it parameters. Now, the parameters property, the value of it is actually a JSON schema object. So JSON schema is a specific way using JavaScript object notation to describe the shape of something, the schema of some data structure. And it has a particular syntax and a particular flavor, and you can go down a whole rabbit hole with JSON schema. But that's the thing to remember when you're thinking what goes in this parameters property. It's the JSON schema that describes the inputs to your functions or your tools. .NET has a really cool feature that was added in .NET 9 that makes generating this really, really easy, and I'll show that when we implement this in our code. But if you didn't have the ability to use that .NET feature, you would just describe this by hand, right? You literally write this out in an object format and serialize it to JSON when you send your request to the API. Now, the other important thing to remember is kind of the overall process here. And Gemini has a really nice, the Gemini API docs have a really nice diagram that just drives home the point that I was making, that remember, the functions or tools are not run by the LLM. The LLM provides inputs, and then your system, your application, the thing hosting your agent actually runs the code. So the first thing you do is you send your response with your function definition. Gemini takes that, it predicts what tokens it wants to output, what does it want to do next, right? It reasons about how it should accomplish whatever the prompt was given, including the function definitions. And if it decides that it wants to use one of those functions that you've included, it will then return a specific response that includes the name of the function that it wants to call and the arguments it wants to call. It's then up to your code, the code that's hosting your agent, to parse those arguments, find the correct function, find the correct tool, and then call it with those arguments. The result of that function call can then be given to the LLM, again with that original prompt. So you can think of this like as an alternating conversation. So you send a prompt, the LLM sends back a request to call a function. You call that function, your code, or you, the user, send back a function result, and then the LLM responds to you again with another result. Now, that result could be another function. It could be the final answer in text format. This loop could go on for as long as you want it to go on, or as long as the model wants to keep calling tools or keep calling functions until it arrives at a final answer. So let's go through the API and how it represents each of these pieces of data. So again, at the top level, we have our content, which we've already done. The tools is what we need to add. This is going to be an array of tools. A tool can have a property on it called a function declaration. This is where we're going to put an array of the functions we want to expose to the LLM. And then the next key concept we need to remember is how we communicate what the model needs to generate, right? The inputs to the function is by giving it a parameters object that is the JSON schema of the inputs to our function. And then last but not least is how do we communicate back and forth to the LLM and the LLM to us when it wants to use a function and when we want to respond with the result of a function. And the way the Gemini API does this is it uses the existing piece of data that's on a object called a part that basically says, hey, the data for this part could be a text, right? This is just it sending back a response in text, or it could be the request to use a function call, which is what the function call property represents. Or in the case of us sending a response back to the LLM, it could be a function response, which is something we'd create and we would hand back. So that's basically this loop. If we go back to this diagram, this loop is basically what we need to implement in our code. Give the ability to define a function, send it to the LLM calls that function, we handle it, we execute the function, and then we return a function response. All right, I know that's a little bit longer than I intended going on about the conceptually what we're doing, but now we'll actually dive into code, and I think this will make a little bit more sense. And lucky for us, .NET has some really cool features that make this pretty easy to implement in simplistic cases. Now, granted, if you were implementing this on a library level or a production level, you may get more sophisticated, more complex, something that's a little bit easier to work with and extend over time. So just to set the stage, where we are with our agent in a file implementation is we basically have the ability to run this app, to provide a, let's say, .NET index.cs, to provide an input to the agent. Can you tell me what your name is? And then we have the ability to handle the agent responding to our user input. It takes a couple seconds to run the inference. Obviously, we're dealing with large language models, but after a minute, it should respond to us. And there we go. So and it's also responding to us like Yoda because the prompt we have attached to our agent is basically, hey, you need to always respond like a helpful assistant, but you want to speak like Yoda from Star Wars. All right, so now the first thing we need to do is we need to actually create a tool or a function that the LLM could use. In this case, because our implementation here is very specific to just like a helpful assistant agent, I'm actually going to include something that historically LLMs are pretty bad with, and that is math. Historically, LLMs are not super great at doing math. Now, some of the newer models, there's also some specially trained models that actually are pretty decent at it. However, in this case, let's just assume we're dealing with a dumb LLM and we need to actually provide it with a tool to do math better. In this case, let's implement something like a calculator. Now, I know this is kind of pedantic and kind of contrived, but it'll be really helpful to drive home the point. So what we're going to do here is we're just going to come down below our console.write line. And let me put my terminal away for a second. And we are going to implement a static function, right? We're just in a single file here, top level statements. So this function will return a decimal. We're going to call this function calculator. And then we're going to need to give the calculator something in order for it to actually perform a calculation, but that'll come in just a second. And then the calculations I'd like to be able to support here are actually pretty simple ones. We're just going to do plus, minus, times, and divide. So let's actually use some syntactic sugar here that C# gives us. And let's add a switch statement here. Actually, let's not do that quite yet. Let's define what our calculator should actually take in. Then we can do our switch statement. That'll look a little better from an implementation perspective and make a little bit more sense. So what does our calculator need in order to run a calculation? Times, plus, divide, all those things. Well, what it needs is it needs the two things you want to operate on. What are the two things you want to multiply? What are the two things you want to add? What are the two things you want to subtract, etc. And then it also needs the operation or the operator that you actually want to run, right? What do you want to calculate? So in this case, I'm going to define a new model or a new record that represents what I'm going to call a calculation. I know, super original, awesome at naming. Don't give me too hard of a time. And I'm going to call this decimal, and this is going to be operand 1. And we're going to have another property here called decimal operand 2. And then the final thing I'm going to have here is I'm just going to have a string. Whoops, come on, Visual Studio. A string, which we're going to call the operator, or maybe we call it operation. And our calculator is always going to need a calculation, right? Pretty straightforward. Now, what we want to do next is we want to actually implement this calculator function. So I'm actually going to use a switch statement to do this. Switch statements are really nice in C#. So we're going to go switch calculation dot operation. Whoops, flip those. Calculation dot operation. And we're going to say switch on this. And based on what you get here, we're going to do some stuff. So we really only want to support 4 operators. So we'll say we want to support plus. We want to support, what else do we want to support? We want to support, I guess that should be a comma there. We want to support minus. We want to support divide. And we want to support times. And then if we get something that we haven't explicitly handled, we will just throw an exception. Now, ideally, you'd probably do something like return a specific result, or maybe you'd have a specific exception type that you would catch, like a tool use exception or something like that, that you could then transform into some meaningful feedback to the LLM. But in this case, we'll just say unsupported operation, like that. And then up here, the way to implement these are actually pretty straightforward. So this will just be calculate operation, calculate operand 1. We'll add to calculation.operand 2. And we'll do the same thing here. Calculation.operand operand 1 minus calculation.operand 2. I think you can see where this is going. Operand 1 divided by calculation.operand 2. Obviously, there's probably a special case there with division that we should handle, but we're just going to pretend like that doesn't exist right now. So multiply that by operand, what do we want to do? Operand 2, there, just like that. And so now we have our calculator function. Now, at this point, C# saying, hey, you're not using this calculator function, why the hell does it exist? Well, it exists because we need to actually use this to provide some information to our LLM. So what we need in order to provide this to the LLM is the first thing we need to add an array to our generate content request that allows us to provide a property that we are going to call tools. And we will say this is an array of tools, which I haven't yet defined. An array of tools, like that. And then our tool, again, these are just types that are coming straight from the Gemini API. So the tool can have a property that we're going to call JSON, or whoops, put this on the property because we're using a record. JSON property name is going to be function declarations, like this. And this is going to be called, let's call this function declarations. And this is going to be another array of a type, which we again haven't implemented yet. We'll call it function. So we'll come down here, and now we'll implement another type called function. And what does function have on it? So function has, we go back to the Gemini documentation, a function well, that's a function call. Where's our function reference? So a function declaration looks like this. It has a name, it has a description, it has this behavior property, which it only supports one value, so it's optional to begin with. And then it has parameters or parameters JSON schema. Now, these in the Gemini API are basically two different ways to express the parameters. One, they support different schemas. We're going to use this parameters JSON schema because we want to stick with the JSON schema format. This uses the OpenAI specification. We're going to use the JSON schema one. So we need to actually define these properties on our function in our code. So let's go back to our code here and let's add those properties. I know, stick with me. I'm looking at the time and I'm getting a little concerned that this is going to be much longer than what I thought, but we're gonna keep moving at a clip here. And I think this will be beneficial for everyone, especially for you if you've been super interested in how exactly this is all done under the hood. So what do we need? We need a name. So we'll say string name. We will have another property, which we will call description. That, and we will have a string of description. And I don't know why Visual Studio always wants to add an extra line there. Property, we will say JSON property name, and this is going to be parameters, and actually it needs to be parameters JSON schema is what we want, to be clear. Like that. And we'll call this one, I'm just going to call this one parameters. I know the JSON name's different here, but for brevity's sake, that's what we're going to do. Okay, so now that we have a way to represent our function, we need to actually supply this as part of our request. So this is where it comes down to, okay, how do we communicate this? Now, the easiest way is to just come up here to our generate content request. And for starters, we'll just supply an empty array. However, we'd like that to actually be populated. So what we'll do here is we'll say we want a new tool, and that tool again is going to start with an empty array of functions, but we'd like this to actually have a calculator function declaration. So let's go above our request and let's say var calculator function. And this is going to be a new function, right? Just like we defined below. And what does a function need, right? A function needs a name. So we'll just use good old name of, right? And this is where some of the powers of C# really start to show themselves. This ability to like not use just magic strings, but to use strong types and use reflection or things that are supported via reflection to actually extract the metadata that we want to use to actually inform the LLM of the code that we've written without having to maintain two different sources of truth, right? We have the actual code that implements the function, and we have some stuff that describes the function to the LLM. We can sort of derive one from the other because of C#, the way C# supports reflection over its static type system. So we're going to say calculator, so name of that static method. We're going to give it a description. In this case, let's call this a function that performs basic arithmetic. Now, the important thing to remember with all the LLM providers is this information that you're sending to whatever LLM of choice is going to be used to help the model make a decision. So a good name and a good description are important. They're not just throwaway things because, again, all of this text, all of these tokens are going to help the LLM reason about what is this thing, how should I use it, when should I call it, what should be the inputs to it. And then the final thing we need to do is we need to supply some parameters. So this would be our parameters JSON schema. Now, at this point, if we look back at the docs, this is where you probably are thinking, man, this could get really heady, or really difficult to communicate again and again this JavaScript object notation. So if we were to do this by hand, obviously in C#, we would have to do something like this where we say JSON serializer, right? We'd have to bring in that namespace, and then we'd have to say serialize, and let's say a new anonymous object that has a property of type, and that's equal to object, and you can kind of see where this is going, right? But this is where, again, C# has some really cool features, one of which was introduced rather recently in .NET 9 under the system.text.json namespace. They actually have a JSON schema exporter, so you can actually reference types from your C# code and get a JSON schema representation of it. So the way you do this is you are going to new up a new JSON schema exporter options object. So you'll say var exporter options equals new JSON schema exporter, right? So this is again under that exporter options. So this is again under that same namespace that everyone's come to know and love, system.text.json. And we're going to new up one of these. And first thing we're going to do is we are going to use that options object in some serializer options. So what we'll do is we'll also new up var serializer options, which is equal to new JSON serializer options, and we'll just give it the defaults for the options class, but we will set right indented true so we can inspect the output a little bit easier on the terminal. And then what we'll do is we'll use those options to get the JSON schema as node. So that's a method call. So this is where we're going to say var calculation schema is equal to serializer options dot get JSON schema as node. This is the method we want. Get JSON schema as node. We'll pass in our type information. So we'll say type of calculation. And then we'll also pass it in the exporter options, because that will allow us to give us control over how things are exported in a little bit. Now we can pass this calculation schema to our function. Now our function is not going to be happy because I failed to type this properly, this should be a JSON node. And I'll have to bring in a namespace for that. But that's going to fit the return type of our export call. Our get JSON schema as node call matches that type. Now, whenever the calculator function is serialized, we'll actually get the proper JSON schema. So let's actually do that real quick. So we'll comment this out here. And we'll comment out these lines out above where we're getting the user input. Whoops, not deleting, just commenting it out. All right, now we'll run this and we'll see what this schema looks like once it's exported. So let's do .NET index.cs. And you can see now we have a JSON schema that includes the requiredness of our properties. We have the typing of our properties, right? And so now this fits with what the documentation requires. Now you will note I've got some weirdness with null values included as a type here. We can control this behavior. So real quick, just to kind of remind you what the documentation looks like. If we go back to our parameter description, you'll see now our JSON schema that we're exporting from our code aligns with what the API expects. So we have the required property. We could add the additional properties or the priority order, and we could add that if we wanted to. But just having the required, the property description, and the type should be enough to satisfy what the model needs to make a decision about how to use the tool. However, we don't want that null in there, right? We don't want the type of null. So what we can do is we can come into our exporter options and we can say treat null oblivious as non-nullable, set that to true. And now what we can do is if we run our code again, we should find that now the type here is set just to object. We don't get that weird type that's an array value with null and object, and more closely aligned with what Gemini would expect, or the Gemini API would expect. Now, the one thing we don't have is if we go back here and we look, what we don't have is we don't have a description on these properties. Now, the type is enough to satisfy what the LLM needs, but it would be really helpful if we also had a description for each of these properties. That would help the LLM understand what are these things. So one of the ways we can do this is, again, leveraging this feature in .NET using the JSON schema exporter options, is we can actually implement what's called a transform schema node. This is basically a property that takes a callback that provides us with the context of the node as well as the schema. And so what we can do is we can come in here and we can say, hey, if the context.propertyInfo is there and the context.propertyInfo.attributeProvider is not null, right? So this allows us to access information about attributes on these contexts, on the members for this context. We can say var description attribute is going to be equal to the context.propertyInfo.attributeProvider, and this allows us to say get our custom attributes, specifically the type of description attribute, set this to true so it includes so this will include, if we set this to true, this will include the inherited attributes, which you could set to false if you wanted. And then we'll set this to first or default, like this. And then the last thing we'll do is now if we have a description attribute, right? If we have a description attribute, then we have a description. And if the schema we're working on is a JSON object, like this, right? So that tells us, hey, you have a piece of the schema that is a JSON object, and you also have a description for the property that this object is representing. Then we can say object.insert 0 name of description. So this means that we're going to insert a property onto that object, name description, and then we're going to set the value of that to the description of the description attribute, the description of the description. And if we come back to our code here, now we also need to return that schema, right? So we modified the schema, so we return it here. Now, if we come back and run this again, we shouldn't see a difference yet, right? So I still have the same properties. But if I scroll down here to my calculation type, and I say description, and I set this to, what do I want to set this to? Let's see. We'll say this, the first operand in the calculation. And again, this is a little contrived because I'm sure the model can sort of infer this just by name alone, but it illustrates that, hey, this is the way that you tap into the LLM's ability to understand text, but tie that text to the code that you've implemented for actually declaring the function and the parameters to the function, the operation to perform. And then I can also say the supported operations are plus, times, minus, and divide. So now I've given the LLM even more operation, because right now it's just a string, but now through my description, I've kind of narrowed that to say these are the operations you should actually ever provide. Don't go outside these bounds. Oh, we also need to make sure that we add property to these attributes. Otherwise, this description attribute won't get put on the records property. Like this. Now, if we run our code again, we should see that we now have a description for each one of our parameters, which will help the model reason about how it should generate inputs for our function. Okay, so now that we have our schema being sent, we now need a way to make sure that whenever the model asks to use a function call, we can handle that. We can translate that to our C# code and then actually call that function and handle the result. So what we'll do for now is we will need to implement a model to represent the model asking to use a function. So let's define a new record. We'll call it function call. And for now, it's just going to have no properties, no information, just a shell. And then we're going to define a new property on our part object here. This is going to represent a function call. And we'll say this is a function call. And this can be nullable. And the reason why we're doing it this way, we'll also make this nullable. The reason why we're doing this way is really because if you were doing this in real life, in production, you would probably do some polymorphic you probably have a polymorphic hierarchy here for part, and you would deserialize part depending on if it has text or function call to a strongly typed object. But for the purposes of this video, this will be just fine. So we'll have a part that can have text, or it can have a function call, it can have neither. But a function call is going to have three things. It's going to have a string of ID. It's going to have a string of name. And then it's going to have a JSON object of arguments. And we'll just go ahead and give these also their corresponding JSON property name. So this will be JSON property name ID. And this will be property JSON property name of name. And then last but not least, we will have args. And you may be thinking, well, where did you get all this information, Stephen? It's just, again, harkening back to the Gemini API's specific implementations. If we're looking at a function call, this will be returned by the LLM, will have this structure. It'll have ID, name, and arg. So instead of text, they'll give us a function call back. So we need to make sure that we can handle that and deal with that when we deserialize the part. So if we come back up to our code now, we should be able to say something like, instead of just saying, hey, hey, what's your name, and just assuming that the model's always going to just give us back text, we need to now look at each individual part and say, is this part text or is this part a function call? If it's a function call, we need to actually call that function. So let's go ahead and add some logic for that now. So we'll say if content, let's say, if content is null, right? Then we know something went wrong. So we can say console.writeLine, and we'll pretend like we're the agent, and we'll say something went wrong. And then we'll say for each var part in content.candidates, right? The first one, .content.parts. So for each part, we will loop over and we'll say, hey, if part.text is not null, meaning this is a text part, right? Again, this would be like if you're doing this for real, you'd have an actual text part type you could like pattern match against, but this will serve just fine for now. We'll say console.writeLine, and instead of all that dot access, we'll just say part.text like this. Otherwise, we'll say if part.function call is not null, we'll handle the function call, right? So what we'll do is we'll say console.writeLine, and again, we'll pretend like we're the agent, and we'll say agent use the part.function call .name. I need to, right? So we're pretending like we're the agent right now. This is not actually being handled by the LM. This is our code doing this. So we'll say use the calculator function I need to, and then we'll actually use it. So in this case, this will happen pretty fast, but you can imagine this could be called to a third-party system or some asynchronous work. So it could take a minute. So we'll check to see, hey, is the function call.name equal to the name of that calculator function that I use to describe the tool the LM could use? We'll say, okay, great. Well, what we want to do is we want to get the calculation then from the call's arguments. So we'll say equals part.functionCall.arguments, and then we'll deserialize this because this is just a JSON object. We'll deserialize it to a calculation using our serializer options from earlier. And we'll say, hey, if we were able to deserialize that, we'll say var result is now going to be equal to that calculator tool called with the calculation that the model gave us. And then we'll print that. So we'll say console.writeLine agent, and we'll say the result, the answer is. Because again, we're trying to talk like Yoda. And otherwise, we'll say console.writeLine agent, and we'll say, actually, let's just say agent unable to use function I was, like that. Now, granted, all of this can be improved upon, but this is, at the simplest case, now we've done a single turn, right? We're handling a single turn still. We send a response, but now that, or we send a request, but now that request has information about a tool. The LLM's like, cool, gotcha, I want to use a tool. Here's a tool back. Then we're executing that tool, and then we're just printing it out to the user. So we're not actually taking another turn. We're not actually sending it back quite yet. That will come in the future. But for now, I just want to show that we are actually communicating a tool to the LLM, and that LLM can actually request to use it with some inputs. So let's do a simple demo here. Hopefully this will work, and I won't have made a liar out of myself. But let's actually try to run this again. So we'll say .NET index.cs. And I got some weird terminal look there. And instead of saying, what is your name, we'll say, what is 2 plus 2? Now, my hope is that the LLM will be able to say, hey, he wants to run a calculation. Let's parse that out, and let's use that tool that he gave us. So let's see what the LLM does. So you can see the LLM gave us a little bit of text back, and it said, hey, calculate 2 plus 2, I will. I'm going to use the force of the calculator, I must. The calculator is the function it knows about. Then here, this is actually our code, right? We're pretending to be the agent at this point to form a final response, but this is our code. It says, hey, the agent asked to use, or the LLM asked to use the calculator function, and then we can see the result of that calculator function was actually 4. So it actually supplied us with the correct operation of plus and with the correct operands of 2 and 2. Let's try that one more time just to kind of drive home the point, but this time we'll do .NET index.cs, more weird terminal. Let's say, what is 2 times 2? Just trust me, it's there. My terminal would cooperate. And let's hit enter, and let's see what the model does. So we can see again, it says use the calculator function I need to, which is our code. So the model didn't actually give me back any text to print out. It just said, hey, I just want to call this function immediately. That's the model's probabilistic nature. Sometimes it's going to give you text with a function call. Sometimes it's just the function call itself. And in this case, we're just calling 2 times 2, which is 4 again. So there is our initial implementation of tool use. Now, you're probably looking at this and saying, okay, well, we didn't implement that full multi-turn diagram that's shown in the Gemini API docs, and we will. We're going to do that in the next video. I don't want us to get us too far ahead of us, and this video is already long enough as it is. But what we're trying to get at here is just, again, driving home the point that to make an agent actually useful, it has to interact with the world. So we have to provide it with functions and tools. And this is how we do that. We implement some code ourselves. In this case, we implement a calculator. Then we inform the LLM about that calculator and what the requirements are to call it in our code. And then we allow the model to request to use it with inputs that satisfy the signature of our code. And then we call it, and we handle the result. In this case, we're just pretending like the agent and printing it for the user. But in the future, what we're going to do is we're going to actually stick this into a full loop where we can handle multiple turns back and forth and multiple chances for the LLM to actually ask to use function calls again and again and again, all in order to build a final response to the user. Okay, I hope that was helpful. I'm really sorry for the length of this video. This took way more time to implement and explain than I had anticipated, but I appreciate you bearing with me. If you found this helpful, please leave a comment. I'd love to hear from you, or find me on Bluesky. Otherwise, I hope you guys have a great rest of your day, and I'll see you guys in the next one. Bye.